In this video, we're going to go through a series of problems that explore the relationship between time and money. Most of the videos are going to build off of this expression where F equals a future bank balance, loan balance, a future amount of money. P is a present amount of money. I is an interest rate. So the units here are dollars, but the units here are percent per unit time, typically year. If no other time is specified, it's typically year. And N is the number of years, or it could be months if the interest rate is expressed in terms of month. N and I must be, in this formula, expressed in the same time units. You might notice that if you have a bank balance that gains interest, it'll be worth more in the future than in the present. So the amount of interest that you collect, F minus P, equals amount of interest gained over this time period. And that's what this question is asking. Ashley invested $5,000 in a mutual fund with a nominal interest rate of 4.8% per year, compounded yearly. So the interest rate is percent per year, the number of compounding periods is equivalent to the number of years, and how much interest would she earn after 2 years? We could take a look at this problem and say, terrific, F equals 5,000, 1 plus the interest rate raised to the 2, and think that this is going to be the answer. It's not the answer, because what we're really asking for is not the future balance, but the difference between the future balance and the present. So in this case, F minus P is going to equal the same expression that we got up here for F, 5,000, 1 plus the interest rate, compounded for 2 years, minus the initial 5,000. Put your answer in the comments. See what you get. This last bit, how much interest would she earn, is one of the key things that you have to catch when you're taking your fundamentals of engineering exam or you're taking a multiple choice test, because this answer, the wrong answer, is likely to be offered as one of the choices on the multiple choice exam. It's a typical mistake that people will make, not reading the problem closely enough and missing the fact that it's asking for the interest, not the future value. So reading the problem carefully and identifying the unknown, understanding how the unknown will be represented mathematically, is key to getting the right answer and demonstrating your knowledge. Let's see what the next problem looks like. Here, we have a continuous compounding problem, and the formula is different. Future value equals present value, but continuous compounding uses E, or E raised to, sometimes abbreviated as EXP. And here is the interest rate and T. T equals time, typically, again, years, but it doesn't have to be, and I in percent per year, where F and P are still measured in dollars. Eric opens his savings account, the annual interest rate of 2.7%, so that's percent per year. If he deposits $6,000 to the account and the interest is compounded continuously, how much interest will he earn after 4 years? Again, it's not asking for the future balance, it's asking for the amount of interest he's earned after 4 years. So we're going to take the 6,000 E raised to the power of 0.027 times the 4 years minus his initial balance of 6,000, and that's going to equal the amount of interest that he's earned after 4. And here's something curious. When we were using the interest rate in the previous problem, we had to add 1 to the interest rate. Interest rates are generally less than 1, so if we were to take 0.0048 and square, it would get even smaller. Cubed even smaller. We add 1 because the future balance is going to be larger, not smaller. When we're using this formula, because the interest is not continuously compounded, we must add 1 to the interest rate before we calculate the future value. It's confusing because if you were using the same pattern, you would add 1 to the interest rate for the continuous compounded formula. Don't do it. You just plug in the interest rate I to the t. And I won't go into the reasons why it derives this way. I'm going to remind you that when you're using the continuously compounded formula, you do not add 1 to the interest rate. Use this formula instead. Put your answer in the comments. Let's see what we have next. This is a much longer one, and the fact that it's long makes it intimidating, but we're going to use the same formula we've always used. 1 plus I, well, the same formula from the first problem. Here we have two interest rates, the 3.3 and the 5.1. We have two balances. 3.3 goes with the 1200, 5.1 goes with the 1800, and N is 6 years. What is the question asking us? How much money will she have? That's a future value question. Not saying how much interest has she collected after 6 years. What will be the balance of these two accounts? The reason that there are two is because the question wants to test you for a misconception. It's a common misconception that you could average these two interest rates, 5.1% plus 3.3%. Well, that's an average of 4.2%. That's not the way interest rates work. Instead, you have to set up two equations and add them together. There will be two terms. In this case, it's 1200 times 1 plus 0.033 to the 6 plus the 1800, 1 plus 0.051 to the 6. That equals the future value. You may not average the interest rates. You may not multiply them by the total balance. You must keep them in separate terms. Put your answer in the response. A loan of $10,000 is made today at an interest rate of 15%. Percent per what? It doesn't say. When the interest rate, when the units of time are absent from the interest rate, assume percent per year, not per month, not per day. Assume that it's annual compounding because that's the convention. The first payment is made of $3,000 4 years later. The amount that is still due. The amount that is still due is asking for F. So we have this formula, F equals P, 1 plus I to the N. We know N, we know I, we know P. The wrinkle in this problem is the $3,000. Let's break the problem down into two steps. The first thing we want to know is what was the balance of the loan right before the payment was made? That's going to be $10,000, 1 plus 0.15 raised to the 4. Right before the $3,000 payment was made, this was the balance. And then $3,000 was paid. Put your answer in the response. Let's see what the next problem has for us. This one is running time a little backwards. It gives you an F and it's asking for a P. Let's take a look at how we can figure that out. Mike has $4,864.77 in his money market account right now, currently. The annual interest rate was 3.9%. That's I. The interest is compounded once every 2 weeks. That's going to be important to know. We've only done annual compounding up till now. How much money was in his account 2 years ago? The way compound interest works is you get a growth curve that is concave up. Suppose that this was the amount 2 years ago, and this amount is 4,864.77. So we're here. If we were to go back in time, the question's asking, how much did Mike start with? And this bit about compounding every 2 weeks is an interesting wrinkle. I'm going to show you how to do it on a per week basis. Same formula, F equals P, 1 plus I to the n. But this time there are 52 weeks in a year. We're compounding every 2 weeks. There will be 26 compounding periods. It's 2 years ago, so n is 2, but we're going to multiply by the 26 compounding periods. It's a little bit different equation. When we're compounding, we're going to use a different form of the equation. F equals P, 1 plus I over n raised to the n times t. And I'm rewriting it a little bit differently than I did here. N will be the number of compounding periods per year. When the number of compounding periods is 1, annual compounding, then n is 1 per year. T is the number of years. So you're beginning to see how this works. We would put in 26 compounding periods a year times 2 years, 1 plus 0.039 divided by 26, 4,864.77 is his future value. What is P? Put your answer in the response. We've got a few more to go through. How much money must be invested at a 10% effective annual rate today to have 10,000 in 5 years? It's another one of those backwards problems. We're going to take the same basic equation. This time we'll go with the more general form that we discovered in the last problem. Effective annual rate means I is 10% per year. And because it's an effective rate, and it's 10% per year, annual is per year, because it's an effective rate, we don't worry about compounding periods. N is 1 compounding period per year, T equals 5. How much money must be invested today to have 10,000 in 5 years? So this is the future amount. 10,000 equals P, 1 plus 0.10 raised to the 5. Put your answer in the comments. We're going to keep going. We're a little more than halfway through this set of problems. Compute the present value of a perpetual stream of annual $2,333 payments using a discount rate of 10%. There's a difference between a discount rate and an interest rate, and we haven't seen this yet. For the discount rate, I'm going to use R. But this problem raises a lot of new issues for us. What's the difference between a discount rate and an interest rate? We use an interest rate when we're starting with a bank balance that grows over time. We're moving forward in time from present to future. Even if we're given a future and the problem is saying, well, what was the present 2 years ago? Think about this interest rate as being collected or charged, collected on a balance, collected on investment, charged on a loan, moving forward in time. We use discount rate when we're going the other way in time. So when the problem, they're interchangeable mathematically, but we think about them when we're anticipating what we would pay today for a future value. We're thinking about discounting that future value. And the weird thing is, typically we think of time going forward to the right, not going forward to the left. When I drew the graph about how a bank balance grows, time is going forward and F is larger than P for positive interest rates. The way the discount rate works is The further forward the f, the further away it is in time, the less valuable it is today. $1 million in 10 years is not worth $1 million today, and $1 million 100 years from now is worth less than $1 million in 10 years. So the first thing we notice about this problem is it's using the word discount rate instead of interest rate. Mathematically, they're exchangeable, but we conceive of the problem differently. At discount rate, time is running backwards, and the shape of our discount curve is different. It's the reciprocal of the shape of our interest rate curve. Keep that complexity in mind. A perpetual stream of payments calls to mind a different formula. There's no F anymore. Instead, these annual payments are going to be represented as A. That's the $2,333 a year. And perpetual means it's paid forever. N equals infinity. We do have a formula that relates P equals A over R, 1 plus I to the R minus 1 all over 1 plus, not to the, that's R, 1 plus R to the N over 1 plus R to the N. So we have this fraction here, and we have A over R, but N is infinity. And this creates quite a problem of evaluation. 1 plus R to the N, when N is infinity, is going to be infinity. 1 plus R to the N with N infinity is going to be infinity. So we have an infinity over infinity problem. But think about infinity minus 1 over infinity. Because these are identical, when they get very, very large, this entire term is approximated as equal to 1. And in fact, the limit as n approaches infinity is 1. The perpetual stream simplifies to P equals A over R. Despite the complications that we have of the perpetual and N equals infinity and the discount rate, we have the easiest formula yet. A is 2,333. The discount rate R, 0.10. P equals, this one you can do in your head, and there's no reason to put your answer in the comments. How many years will be required for 10,000 invested at 8% per year, compounded annually to double in value? Well, one way to think of that is F equals P, 1 plus I to the N. Here, it's giving us P, that's the 10,000. Well, double, it's giving us F, that's 20,000. It's giving us I, 0.08% per year. It's just asking you to solve for N. And we can do that exactly, but that's not really what the question wants to know. This question is testing your knowledge of the rule of 72 because it's asking you to approximate about how many years. And the rule of 72 is interesting. I'm going to go back to F equals P to the EIT, the continuously compounded formula, so we can see where the rule of 72 comes from. F over P is 2. How long does it take? How many years, that's T, will be required for 10,000 to double? F over P is going to be 2. We've just divided both sides by P, and that equals E to the IT. We want to solve for T. How many years? So we're going to take natural log of 2 equals natural log of E to the IT. And of course, the natural log of E raised to the power is just IT. When we solve for T, T equals ln 2 over I. Well, the ln of 2 is 0.69 over the interest rate equals T. Once we know the interest rate, in this case 8%, we would take 0.69 divided by 0.08, and that would give us the time that a continuously compounded investment would be required to double. So why is it called the rule of 72? Because people can't do math in their head with 69. 72 has a lot of more factors than 69 does. So we say t equals 72 over 8%. I've moved the decimal place 2 places. Interest rate is expressed not in terms of a decimal, but in terms of percent. And the answer is 9. Why 72 instead of 69? I mentioned that 72 is a way of yielding an approximate answer that many people can do in their head because 72 has so many factors, 3, 4, 6. But there's another reason. Most interest is not continuously compounded. Most interest is compounded either monthly or annually, which means we go back to this old formula. And this one grows more slowly than continuous compounding. When you're only compounding yearly or monthly, it takes longer. So 72 is an approximation. The exact answer would be 69 in this numerator. But when we're only compounding monthly or annually, it's going to take longer. 72 is a convenient way, a rule of thumb, for understanding how long it takes to double an investment, and that's what this question is testing for. Just a couple more. Let F be the future worth, we knew that. P be the principal invested, I the effective interest rate, we knew all that, and the number of in which of the following formulas are these quantities correctly related? If you have been paying attention, then you know the formula looks like this. The more general form is like that, when n is the number of compounding periods per year. There are any myriad of ways to confuse or mistake this formula that might trip you up. I recommend you work enough problems to memorize it. Now we're going to get into what does it mean by effective, because the formula for compounding periods here that I gave you, where we'll divide the number of compounding periods per year, is for when I is stated as a nominal interest rate. When I is stated as an effective rate, the simpler formula applies. And that seems like a lot to keep track of, where n equals number of years. We could also put t. We're going to get into this difference between effective and nominal in the very last question. Nominal comes from the same root word as name. So when a bank advertises that a car loan is available at a special discount rate of 5.5%, they're talking about a nominal rate, a nominal dimension at the lumberyard. When you buy a 2x4, those are nominal dimensions. The real dimensions are 1.5 inches, at least in Canada and the United States, by 3.5 inches. They start with a 2-inch by 4-inch at the lumber mill, and then they remove 1/4 inch from all sides to give you a smooth piece. The difference between the nominal, the name of the piece, and the real dimensions is confusing. The difference between the name of the interest rate and the real interest rate that you collect is confusing. The difference between nominal and effective. Effective is what you actually owe, or what you actually collect, is compounding. And I introduced you to the way that we account for compounding in this formula. This formula uses a nominal interest rate for I and a number of compounding periods other than one to adjust from the nominal to the effective. I'm going to be more specific now. The nominal rate, 5.5, we can get an effective rate. We can convert that to an effective rate like this. 1 plus I, where I is expressed as the nominal, over n to the n And then we got to subtract out the 1. So the effective rate is 1 plus the nominal rate divided by the number of compounding periods per year raised to the number of compounding periods per year minus 1. Something really interesting happens when the number of compounding periods approaches infinity. That's called continuous compounding. And it will be interesting to see if you could derive the formula that we found earlier, e to the I t.